Welcome everybody to this video. In this video we'll talk about the oxidation reduction reactions. So as a brief introduction, what are the main objectives of the video? You will be able at the end of the video to define what is an oxidation, what is a reduction reaction. You will be able to distinguish between the oxidizing agents and the reducing agents, as well as you will be able to write the redox couples and to draw the electrochemical classification axis. In other words, you will be able to classify redox couples on the electrochemical classification axis. Hopefully, you will be able to do that. Now, let's start with the first. In this experiment, with the first slide, in this experiment, we have Zn strip dipped in CuSO4 solution, which is aqueous. As you may notice that the CuSO4 solution has blue color. Okay, the CuSO4 solution has blue color, and you can see this through the beaker that is blue color. When we dip the Zn strip inside the CuSO4 solution, after a while we started to notice that the Zn strip decreases in mass, and the formation of copper solids, okay, the formation of copper deposits, and the blue solution starts to fade out. Okay, this means that we are not having any more CuSO4 inside our solution, because the CuSO4 solution is blue, and when the blue color starts to fade out, that means that we don't have CuSO4 anymore. Another observation is that it liberates heat, so it's exothermic. The reaction is exothermic, so it's obvious that we have in this experiment we have a reaction. Now let's talk about the reaction. We've started from, as you can see, we added zinc strip to CuSO4, so we have zinc strip to as a solid plus CuSO4. So what's going on? Let's talk about the CuSO4. CuSO4 actually, the dissociation reaction of CuSO4 dissociates in water to Cu2 plus ions plus SO4 2 minus. Well, SO4 2 minus, I'm not really interested in SO4 2 minus. It's a spectator ion. It is involved in the reaction, but right now I'm not really interested about SO4 2 minus. So Cu2 plus, so we have actually let's write it this way, that I have Zn as a solid plus Cu2 plus as aqueous, right? I'm getting out Cu as a solid plus Zn2 plus as aqueous. This is the reaction. Now let us write half reactions. We say half reactions to know exactly what's going on in every element. Now you may ask me, how did you notice that we have Zn2 plus in the solution at the end of the solution? Well, we have several techniques. If you need to know about these techniques, please let me know. I can explain that to you. But we have several techniques to test if there is a Zn2 plus inside our solution or not. And we did that, and we noticed that we have Zn2 plus inside the solution. So if I want to write the reaction that is occurring here, it's Zn as a solid plus Cu2 plus in the aqueous form. It's giving us Cu as a solid plus Zn2 plus in the aqueous form, which is exactly over here. It's written over here. Okay. Now I want to look you want to divide up the reactions to the metal. So we started with Zn as a solid, right? And then we ended up with Zn2 plus as aqueous, right? So what's interesting here is that the step from here to there requires that we have to put here 2 electrons, requires that Zn loses 2 electrons to become Zn2 plus at the end of the reaction. So we started with Zn. Zn loses 2 electrons to become Zn2 plus. This is first. Now second, we start with Cu2 plus and we ended up with Cu as a solid, right? You can see the red deposit of Cu here. Okay, so here's the red deposit. We're talking here specifically. So Cu2 plus becomes Cu. The jump from Cu2 plus to Cu requires 2 electrons. So Cu needs to gain, Cu2 plus to be more precise, Cu2 plus ions needs to gain 2 electrons to become Cu. Now, here we can say that Zn loses 2 electrons, Cu gains 2 electrons, Cu2 plus to be more precise. That's Cu2 plus. Cu2 plus gains 2 electrons to become Cu. Now, what's going on here? It's obvious that Zn loses the 2 electrons so that Cu was able to gain these 2 electrons. There were transfer of electrons from Zn to Cu. Okay? So Zn loses 2 electrons to Cu so that Zn becomes Zn2 plus and Cu2 plus gain 2 electrons from Zn to become Cu. Okay? So there is transfer of electron, and this the process where elements lose electron, we call it oxidation. And the process where elements gain electrons, we call it reduction. Now, why do we call oxidation a half reaction? We don't say that it's a complete reaction, or we say it's half reaction. Oxidation, half reaction. Also, we say reduction, half reaction, because oxidation and reduction occurs simultaneously. So that the total reaction is here. This what we call the redox reaction, redox total reactions. This one, okay, this one, Zn becoming Zn2 plus 2 electrons is oxidation half reaction. So let me write it here. So okay, let me just cover this slide. So the observation was the thermometer indicates the rise of temperature. The blue solution of copper sulfate starts to fade and starts to disappear. The red deposit of copper metal appeared on zinc strip, and the zinc strip decreased. So we covered this. Okay, so the interpretation, we have Zn as a solid becomes Zn2 plus aqueous plus 2 electrons, right? We have Cu2 plus as aqueous. It gains 2 electrons to become Cu as a solid. Now here, bear in mind, here is Zn lose electrons, so we say oxidation half reaction, and here the Cu gained electrons, so we say it's reduction half reaction. Why it's called half? Because, as I've mentioned before, the reaction usually occurs simultaneously, so that the overall reaction is, we delete these 2 electrons from here, and we delete from here the 2 electrons, so it becomes Zn as a solid plus Cu2 plus as an aqueous. It's giving us Cu as a solid plus Zn2 plus as an aqueous, and so that we were able to interpret what's going on with the reactions with the beaker at the beginning of the video. Okay, now this is, we call it redox, not half reaction, we call it redox reaction. Okay, so oxidation is the loss of electrons by a chemical species. reduction is the gain of electrons by a chemical, sorry for the typo, chemical species. Now here it's a little bit tricky how the reducing agent loses electrons and the oxidizing agent gains electrons. In order to make it easier to understand, think about it this way. The reducing agent and the oxidizing agent, we'll think about it this way. We have Zn. We started our experiment with Zn and Cu2 plus, right? So Zn undergoes oxidation and Cu2 plus undergoes reduction. Now the question is, what is the agent that allows Zn to undergo its oxidation? In other words, what element triggers Zn to lose electrons? If there is no element wants to gain electrons, so that the Zn will not lose electron. So that Cu2 plus is the agent that triggers Zn to lose electrons. Because of that, we can say it's the oxidizing agent. It allows Zn to undergo oxidation. It oxidizes Zn. Although it undergoes reduction because it gains electrons, but it oxidizes Zn. In other words, let me say it takes out electrons from Zn. That's why we call the one that undergoes reduction is the oxidizing agent, and vice versa. The one undergoes oxidation is the reducing agent. Okay? The one undergoes oxidation is the reducing agent because Zn reduces Cu2 plus. It allows Cu2 plus to take 2 electrons because it loses itself 2 electrons, Zn. It undergoes oxidation so that it allows Cu2 plus to take 2 electrons, so that we call it's the reducing agent. I hope it's clear now. So Zn here, it reduces Cu2 plus, and Cu2 plus here, it oxidizes Zn. Okay, so as I've mentioned, the reducing agent loses electrons, the reducing agent undergoes oxidation, and the oxidizing agent gains electrons. The oxidizing agent undergoes reduction. Okay, you can remember just by thinking of it like vice versa. Reducing agent undergoes oxidation, and oxidizing agent undergoes reduction. But I'm just giving you why this terminology being invoked in the first place. Okay, hope it's clear now. So let's complete. Now, how to write the redox couples? Mainly, every element has its own redox couples. Every element has its own redox couples. It's the way we write the couples. So in this reaction, in this half cell, we have reduction half cell. Let me talk about the reduction reduction half reaction. We have Cu2 plus 2 electrons, it's giving us Cu, right? Now, this is the reduction half reaction that we have. But in some cases, oxidation half reaction, in some cases, this is case 1 and this is case 2. Oxidation half reaction, Cu can lose 2 electrons, can undergo oxidation to become Cu2 plus. Sorry, So Bu2 plus plus 2 electrons. Okay, so first Cu2 plus undergoes reduction to become Cu, and here in this case we have Cu undergoes oxidation to become Cu2 plus. Okay, now this is case 1, this is case 2. This is important to mention that it depends on the situation, it depends on the element, on the counter element, okay, that we have, so that either Cu will undergoes oxidation or Cu2 plus will undergoes reduction. Okay, we will talk about it later, but these are the two half reactions, the two possible reactions that Cu can do. Okay, either oxidation or reduction. If it's reduction, Cu2 plus will gain 2 electrons, and if it's oxidation, the Cu will lose electrons to become Cu2 plus. So copper as an element can undergoes either reduction or oxidation. If undergoes reduction, then Cu2 plus here is what? It undergoes reduction is the oxidizing agent. And the Cu here is the reducing agent. See, the role of copper changes according to the element that it's reacting to. Okay, so how to write the redox couple? This is simply redox couple of copper is simply Cu2 plus slash, we have this slash Cu. How? Cu2 plus, we start with the oxidizing agent and slash reducing agent. As simple as that. So the redox couple of a metal element M represented by Mn plus M is formed by the oxidizing agent Mn plus and then the reducing agent M are related by the half reaction. Okay, so if we want to consider the reduction half reaction of our case, Cu2 plus, okay, here we have plus 2 electrons. Let me just, Cu2 plus 2 electrons, Cu is giving us Cu. So Cu2 plus and Cu are related, these two components, the Cu2 plus and Cu are related through the half reaction. And that's how we write the redox couple. This is how we write the redox couple. So there is a misconception. Again, I'm just gonna write the misconception. So as we've mentioned, that we started with Zn as a solid plus Cu as an aqueous, Cu2 plus, sorry, and it gives us Zn2 plus aqueous plus Cu solid. There is a misconception where students tend to make mistake. If I want just to tell you, write the redox couples of this reaction. So some would write Cu2 plus Zn, or some would write Zn2 plus Cu. Well, actually, this is wrong. Both are wrong because the redox couples belong to the same metal. So if I want just to write if I just told you write the redox couples of this reaction, you would write, we have two redox couples here. We have the Cu2 plus Cu, with the oxidizing agent of copper and the reducing agent of copper, and Zn2 plus Zn. These are the redox couples of this reaction, the reaction that we started with. Okay. Okay, so let's proceed with the material. Now here we have the electrochemical axis, the last idea in this video, and here we have two reactions. Well, the second one, we don't have a reaction when we add Ag and Cu, but just let me, before just complete, talking about this, I want just, if we still remember, I want to talk about something important. If we still remember, the first reaction that we had is Cu2 plus Zn zinc. It gives us Cu solid plus Zn in aqueous, Zn2 plus aqueous. Right, and then we said that Cu2 plus gained 2 electrons to become this is not an arrow of reaction, okay? Cu2 plus gains 2 electrons to become Cu. And then we said this undergoes reduction. Now in this case, Cu, what was Cu, and it becomes Cu2 plus. So Cu2 plus here lose 2 electrons to become Cu lose 2 electrons to become Cu2 plus. In this case, copper undergoes oxidation. So copper can undergoes oxidation or reduction. This depends on what element the copper is reacting to. And that's why when we write the redox couple, the redox couple of copper, we can say it's Cu2 plus Cu, or the oxidizing agent slash the reducing agent. That's the idea that I want just to convey, talking about the redox couples, that each element can have an oxidizing agent and a reducing agent. Each element can undergo reduction or oxidation. That depends on the reaction. So when it was with Zn, what it was with zinc, copper undergoes reduction. But when it was with Ag, copper undergoes oxidation. Now we will talk about this, why we don't have a reaction here. Well, when we added Ag with Cu2 plus, we don't have reaction. There were no reaction. Okay, when we added Ag with Cu2 plus, so we have to really analyze why this is going on. Okay, when we added Cu with Ag plus, we have a reaction. It brings Cu2 plus Ag. The contrast, when we had Cu2 plus with Ag, we don't have the reaction. So we will talk about why. So the silver metal Ag does not react with Cu2 plus. The reaction between the two redox couples is spontaneous when the reagents are Cu or Ag, or when we inverse the ions and metals. So when the Cu was a metal, Ag was ions, we have the reaction. Ag was a metal, Cu was ions, we don't have a reaction. So when we inverse the metal becomes ions and ions becomes metal. In this case, we have a reaction. Okay, so things will become more clear. Okay, so as you can see, if you can still remember the reactions that we had, so Cu plus 2Ag plus, we got a reaction which is Cu2 plus 2Ag, right? And when we had Cu2 plus 2Ag, there is no reaction. Now, I really need to talk about these two things. Why? In the first case, we have a reaction, and let me say this is first. And the second, why we don't have a reaction in the second one? Well, it's obviously copper metal reduces Ag plus. The copper metal was able to reduce Ag plus. Remember, look at the first reaction. Copper was able to reduce Ag plus. When we say reduce, was able to oblige Ag plus to undergo reduction. Let's thinking about this way, to undergo reduction. So we say that Cu reduces Ag plus. Whereas silver metal Ag does not reduces Cu2 plus. Ag wasn't able to oblige Cu2 plus to undergo reduction, and that's because we don't have reaction. But Cu was obliging Ag plus to undergo reduction. So Cu was able to reduce Ag plus, whereas Ag wasn't able to reduce Cu2 plus. This means that the reducing power of copper is greater than the reducing power of silver. Okay, so here we are comparing to the copper metal. Here we're comparing metals: the copper metal and the silver metal. Why? Because we're comparing reducing powers. The reducing powers is to allow others to undergo reduction. This means that they are the reducing agent. So to allow others to undergo reduction, to oblige others to be the agent so that the other undergoes reduction, you are the reducing agent. So we're comparing reducing agents here. So here we have said that the reducing power of copper is greater than the reducing power of silver. So reducing power copper is greater than the reducing power of silver. Okay? Now let's complete. Ag ion oxidizes copper metal. This is one. Another point 2. So Ag plus ion oxidizes copper metal. Whereas Cu2 plus ions cannot oxidize. Remember, the verb is oxidize now. The verb is oxidize. And here the verb was reduce. Okay? So when we compare oxidizing power, we always look at the oxidizing agents. Because what is the component inside the reactant that makes the other element undergoes oxidation? It's those who undergoes reduction. They are the oxidizing agent. Okay? So Ag plus ion oxidizes copper metal, Cu, whereas Cu2 plus ion does not oxidize silver metal, Ag. So the oxidizing agent power of Ag ion is greater than the oxidizing power of Cu2 plus. So here, oxidizing power, let me just write it, oxidizing power Ag, the oxidizing power of Ag plus is greater than the Cu2 plus. Okay? Why we're comparing? So let's read it another time. Ag plus ion oxidizes copper metal. Here we have Ag plus ion obliges Cu to undergo oxidation to lose 2 electrons to become Cu2 plus, right? So Ag plus ion was able to oxidize copper metal, whereas Cu2 plus wasn't able to oblige Ag to lose 2 electrons. To lose 2 electrons if it's 2 by 2, yani 2 by 1, 2. So the Cu2 plus ions were not obliged silver to lose electrons, so that the copper ions didn't oxidize silver metal, wasn't able to oxidize silver metal. And that's clear because we don't have reaction. The silver metal didn't lose electrons. So copper ions weren't able to oblige silver metal to undergo oxidation. So in this case, Ag plus ion is greater than the oxidizing power, has a greater oxidizing power than Cu2 plus. So as a conclusion, Ag plus ions has a greater oxidizing power than Cu2 plus. Okay, so let's complete with the next slide. So Ag plus greater has a greater than Cu2 plus. Okay, this is a greater oxidizing power. This is comparing oxidizing power. Whereas Cu is greater than Ag comparing reducing power. Now if we want to put these two in axes, we're gonna start with the oxidizing power. As we go up, oxidizing power increases. Okay, here we have Ag plus Cu2 plus, because Ag plus is greater than Cu2 plus. Now this is comparing oxidizing powers. Now let's compare the reducing powers. The reducing powers as we go down is reducing power increases. As we go down, the reducing power increases. So Cu is greater, so Cu that is below Ag. Now if you want to combine these two axes in one axis, this is the one axis we're talking about. Here we have Ag plus Ag, Cu2 plus Cu, where here we're comparing oxidizing power and here reducing power. So that's how we form the electrochemical axis. Okay, by comparing oxidizing power and reducing power. So here we can say that Ag plus has a more oxidizing power than Cu2 plus, whereas Cu has a greater reducing power than Ag. So here, the greater the reducing power of a metal, the lower the oxidizing power of its ion, and vice versa. As you can see that because Cu has a greater reducing power, the oxidizing power of its ion it becomes less. So the greater the reducing power of a metal, the less the oxidizing power of its ion. Okay, so let's look here. Okay. Now the spontaneous reaction, this is important here. The spontaneous reaction between couples Mn plus 1 M, this is the two couples, the redox couples, and M2, another metal, occurs between the stronger oxidizing agent and the stronger reducing agent. How this happens? Okay, look, between these two couples, we need to choose the stronger oxidizing agent and the stronger reducing agent. So comparing Ag plus and Cu2 plus, which is the stronger oxidizing agent? It's the Ag plus. And we go to the metals. Comparing Ag and Cu, which has the stronger reducing power, the stronger reducing agent, it's copper. So the spontaneous reaction, whenever we need to choose between two redox couples, the spontaneous reaction should occur between the stronger oxidizing power, which is Ag plus in this case, because it's stronger than Cu2 plus, with the stronger reducing power, which is Cu in this case, which has the stronger reducing power. Now, if we have a reaction, and that's why it didn't work, Ag plus with Cu2 plus, we don't have a reaction because Ag plus is a weaker reducing agent than Cu, and Cu2 plus as well is weaker oxidizing agent than Ag plus. So it wouldn't work. So in spontaneous reaction between couples, M1, between couples like metal, the element 1 and element 2, okay, occurs between the stronger oxidizing agent, you should keep this in your mind, the stronger oxidizing agent with the stronger reducing agent. Okay, now we have something which is called the gamma rule. Ag plus, we have here the electrochemical axis. So how to notice how the reaction can proceed? Through the gamma rule. You start from the oxidizing agent and you come to the reducing agent. This is a gamma. and Cu2 plus gives Cu2 plus and Ag. So Ag plus Cu, we need to form equilibrium, gives us Cu2 plus Ag, 2Ag. This is how the gamma rule works. Ag plus Cu gives Cu2 plus Ag. But you know the cause of how the gamma rule is being invoked in the first place, through the oxidizing agent, the stronger oxidizing agent forming a reaction with the stronger reducing agent. Let's now proceed with this exercise. When forming the electrochemical axis, this not only we don't have to consider only two redox couples. In fact, we have many redox couples. We can place them in the same electrochemical axis. Now let's consider how can we are able through a series of reactions to draw the electrochemical axis, or to put the redox couples inside the electrochemical axis. Okay, so we have this first reaction, Cu with Ag plus. We have a reaction. This is, we talked about it last time, not last time, in the previous slide. So I've said that Ag plus is the stronger oxidizing agent, should be here, and Cu2 plus is weaker oxidizing agent, and here we have copper is a stronger reducing agent, and Ag is a weaker reducing agent. Just remember, this is oxidizing agent increases up, and here down, reducing agent increases. Okay, this is concerning the first reaction. The second reaction is no reaction. It implies the same, it gives us the same conclusion as the first one. Now let's look at 2. Zn plus Cu2 plus gives us a reaction. Cu2 plus should be, because there is a reaction, then Cu2 plus should be the greater oxidizing agent, Cu2 plus, than Zn. Zn2 plus. So we're comparing, when we compare oxidizing agent, we need to compare Zn2 plus. We need to put Zn2 plus. And because there is a reaction, so Zn should be a stronger reducing agent than Cu. Again, oxidizing power increases, and here reducing power increases. Okay, now let's look at the third one and the fourth one. Let's look in FeCu. Here I'm gonna leave this space to write put all the metals. We have here Zn, Fe, Cu, and Ag. We have 4 metals. Okay, so let's look in Fe and Cu2 plus. Fe, Cu2 plus should be the stronger oxidizing agent, Cu2 plus, than Fe2 plus. And Fe should be the stronger reducing agent than Cu. You're getting the logic? I'm looking at, if we have a reaction, then Cu2 plus, I'm comparing it to Fe2 plus. It should be, it should has a greater oxidizing agent power. Okay, because we have a reaction. Otherwise, we don't have a reaction. So it should has a Cu2 plus is above Fe2 plus because it has more power, and Fe should has a greater reducing power because there was a reaction. Okay, so Fe was able to reduce Cu2 plus, then Fe should be below the reducing, should be below Cu, because in the reducing agents, as we go down, the reducing power increases. So this is 1, this is 2, this is 3. Now in the fourth reaction, we have Fe2 plus and Zn. Because we have a reaction, then Fe2 plus should has a greater oxidizing power than Zn2 plus, right? Fe2 plus should has a greater oxidizing power than Zn2 plus. And because we have a reaction, Zn should has a greater reducing power than Fe. Remember, as we go down, the reducing power increases. As we go up, the oxidizing power increases. Reducing agent power, increases. And as you go up, the oxidizing power increases. So we have these four sub electrochemical axes. We have these four. We need to combine them in one big electrochemical axis. So it's obviously that Ag plus has the strongest. Ag plus has the strongest. Now, if we want to say that, we have look. Let's look here. We have Cu2 plus, Cu2 plus, Cu2 plus. So Cu2 plus is below Ag plus. You have something above between Ag plus and Cu. We don't have something between Ag plus and Cu2 plus, or between copper and silver, to be more precise. Then we can here we have Cu2 plus, Cu. Now we need to look at the Zn and Fe. Here we have Cu is below Zn, and Zn is below Cu, and Fe is below Cu. But how to place them? Fe is above Zn as well. Fe is above Zn. So Fe here we have, and both below Cu. So Fe here we got Fe2 plus Fe and Zn2 plus Zn. Okay, this is oxidizing power increases here, and reducing power increases here as we go down. Now there is a question. Okay, I'm just gonna say how I was able to put these four electrochemical axes in one big axis. Look, we have Ag plus. Nothing is above Ag plus. Okay, so Ag plus is first. Now Cu2 plus is below Ag plus, but again, nothing is above Cu2 plus. As you can see, other than Ag, other than silver. If you look at the copper and zinc, copper is above zinc. Copper and iron, copper is above iron. Here we don't have copper even. So copper is the second in our electrochemical axis. Now here we need to compare. Zinc is below copper and iron is below copper. But how can we notice if who is below and who is above? We compare iron and zinc to each other alone. We saw that the iron is above zinc. Okay, so copper, iron, zinc. This is how we arrange elements in the electrochemical axis, or this is how we arrange redox couples in the electrochemical axis. Now I have a question. There is a misconception somewhere that Ag cannot react with the Zn. Some misconception. Yes, Ag plus can react with Zn. You should all the time think about stronger oxidizing power with a stronger reducing power. Ag plus is a stronger oxidizing power than Zn2 plus, and Zn is a stronger reducing power than Ag. We have here Ag plus Zn, we have a reaction. Okay, so I can form the gamma rule from here to there. Okay, I can form the gamma rule as well. Cu2 plus Zn, it gives us Zn2 plus Cu. I can form the gamma rule as long as I have a stronger oxidizing power reacting with a stronger reducing power. Hope that you enjoyed this video, and we will catch up in other videos. Thank you for your watching.